So I want to take the Fourier transform of the function 1 over x squared plus 6x plus 13, okay? And I want to do it using the residue theorem. So again, the first thing I will do is find my poles. So set the denominator equal to 0, and then solve for x. So I get x is equal to minus 3 plus or minus 2i. Now I can see that I have a pole of order 1, okay, it's everything to the first power, you have nothing squared in the denominator, and so we can use the residue for pole of order 1, okay, which says basically that if you have a fraction, the top of the fraction we don't change it, but the bottom of the fraction, so the denominator, we just take the derivative, okay. So the top of the fraction doesn't change, so we still have e to the minus I omega x, but at the bottom we take the derivative of the denominator, so the derivative of x squared plus 6x plus 6x plus 13 is 2x plus 6, okay? 13 is a constant, so it's 0. Okay, so now I can insert my my poles, okay? So minus 3 plus 2 plus 2i and minus 3 minus 2i, and once I rearrange it, I should get minus 1 over 4i e to the 2 plus 3i omega, and 1 over 4i e to the minus 2 plus 3i omega, okay? Yes, so now I need again to be careful about the sign of omega, if omega is negative and if omega is positive. If omega is negative, again, we, as said in the last videos, we need to have a contour along the half circle in the upper half plane. So yeah, so again I can split my my contour integral into two parts, the part along the real axis, so from minus infinity to positive infinity, which will be my original integral, and the path around this circular axis, circular path in the upper half plane, okay. And now we will try to prove that this part number 2, so the part along the circular axis, vanishes as our radius r gets larger and larger, okay. So we'll let again x be equal to r e to the pi I t, and t be between 0 and 1, okay, again because e to the pi t is if t is between 0 and 1, this is half a circle, and that's what you want. Okay, remember that e to the theta I is simply a circle, and so if we have e to the pi I t, and t is between 0 and 1, yeah, we have either e to the 0, so 1, so here, or e to the pi I, which is negative 1, should be here, okay. If t is between 0 and negative 1, that you would have this path that we will examine later, okay. So for the first case, t is between 0 and 1, and dx is equal to pi I r e to the pi t dt, okay. This is simply the derivative of x if x is equal to r to the e pi t, okay. But again, we don't really need it, as in the last videos. We will mainly focus on or exponential decay, so we'll try to get e to the minus infinity to show that the second part, number 2, be it here or here later, vanishes as the radius tends toward infinity, and so we will only be left with the first part along the real axis, and that will be our original integral, and that will be equal to our original integral, and then we will set it equal to the residue theorem. So, okay, so we will say that the contour integral is equal to 2 pi I times the sum of the residues, and so we can evaluate our integral, okay. Yes, which is a Fourier transform, as said. So here for the proof, so we now have everything with respect to t, okay, so t is between 0 and 1, and so we replace everything with x with r to the e pi I t, and dx with pi I r e to the pi I t dt. So again, you can replace everything, but what's important is that you replace the x in the e to the minus I omega x with, you replace this x with r e to the pi I t. Okay, that is important because now you can use Euler's formula. So e to the theta I is equal to cosine theta plus I sine theta, okay? And so this e to the pi t in the exponent, you can replace it with, you can use Euler's formula, so you get e to the minus I omega r times cosine pi t plus I sine pi t. Okay, remember that we have a pi I t, so the I is the I here, but the theta is equal to pi t, okay, if we see it like that. And so now we can rearrange it. We can take the minus I inside. Still the omega r will let it outside because we don't care. But the minus I will be in front of the cosine pt, and we will multiply our I sine pt with negative I. So we will get negative I times r, so negative I squared, so negative 1, so positive 1, okay? So there would be a positive 1 here, okay? Of course, we don't write it if there is a 1, because we can write infinitely many 1. But still, there it's why we have a positive sine pt now, because it's negative 1, okay? And so now, again, our job is to get an exponential decay, so e to the minus infinity. So we know that the radius will tend toward infinity. Remember, a radius cannot be negative, okay, because we cannot have negative geometric distances, okay? So the radius will always tend toward positive infinity, never negative infinity, okay? A negative infinity radius is not possible. So we also know that we assume that our omega is negative, so as seen here. And so now to get an exponential decay, we need to have e to the minus infinity. So we already have our infinity here. We already have our minus sign here. That means that sine of pt should be positive, okay? And that's the case for t between 0 and 1, because as said, the sine is generally along the imaginary axis, okay? The cosine is on the real axis generally. And so if we are in the upper half plane, we already know that our sine will be positive. Also, as I said, if t is between 0 and 1, we will only get positive values for sine, okay? If t is between 0 and negative 1, we would always get negative values. But would be the case for the second case later. Okay, so yes, sine is always positive, omega is always negative, and we have r that tends toward infinity. So we can now be sure that we will get our exponential decay, so e to the minus infinity, okay? The infinity is r. Here, the omega is the negative sign. Sine is positive, and remember that e to the minus I cosine pt is bounded, okay? Because there's an I in front here, okay, that's an I. We don't care about if it's a negative or positive I. We just know that there is an I, so it's something of the form e to the I theta, and we know that that is bounded, okay? That is bounded, okay? So this is a circle of radius 1 generally, okay? So we don't really care about it, okay? That's why we don't talk much about the cosine, because there's an I in front. As long as there's an I in front and that's in the exponent, we don't care, okay? For the e to the I something, okay? Yeah, so we get our e to the negative infinity and we get 0, and thus our second part vanishes as expected, okay? We will do the same proof for the second part in a bit different way, but it's highly similar. So we're only left with the first part of the integral, so along the real axis, so from negative infinity to positive infinity. So our first part is an original integral, that hasn't changed, but our second part is now 0, okay? That's why we have 0. And now we can use the residue theorem. We can set it equal to 2 pi I times the sum of the residues. So we have our 2 pi I here. Remember, we have 2 pi I because we are in a counterclockwise direction, okay? We go like that, okay? We go in this sense, okay? So remember, counterclockwise in math, let's write it here, counterclockwise in math is positive and clockwise is negative. That's why for the second case here, we will multiply by negative 2 pi because we are in a clockwise direction, okay? But we will see that later. So for the first case, we have now our 2 pi I, so positive because we have a counter integral in a counterclockwise direction. And so now we multiply this 2 pi I with our residue. So we only have one residue inside, that is the minus 3 plus 2i, because the minus 3 minus 2i is outside of this contour in the upper half plane, okay? So we only have this residue here, so minus 1 over 4i e to the 2 plus 3i omega, okay? And so if we rearrange that, we get pi over 2 times e to the 2 plus 3i omega, and remember, omega is assumed to be negative, okay? That is highly important. You can already see that this omega here, there is a 2 here, so the 3i we don't care because I said it's again e to the theta I, but there is a 2 here, so we have e to the 2 omega, but omega is negative, so it's 2 e to the minus something, and that's already a good sign because that means that the thing here converges, okay? If omega gets larger and larger, still it will converge, okay? So that's already a good sign, you can check it. If you see that you have e to the minus something is in your result, that's a good sign. That means that you're probably right, okay? If it's not the case, then probably there is a mistake somewhere, okay? Yes. So now for the second part, so now if omega is greater than 0, we will do the same things, but a bit differently. We will have our contour 0 in the lower half plane, and as said in a clockwise direction, okay, we're doing it like that. We still start where minus infinity is, and we'll go like that, and that's why we have a minus 2 pi here, okay? It's because this is negative. Also, it is should be not positive but negative, okay? Yeah. Yes, yeah, so we deal with the same thing, so we split it into 2 parts, 1 and 2, so 1 again along the real axis, so which will be our original integral, and the second part will again try to prove that it vanishes as our radius r gets bigger and bigger. So we set x equal to the same thing as before, so r e to the pi I t. I haven't written it again because it's the same thing, but t is between 0 and -1, again because we are doing like that, okay? We are doing in the lower half plane in a clockwise direction, okay? T would be between 0 and 1 if you would do it like that, but that is only the case for the first case, not the second case, okay? So here t is between 0 and -1, and so we're moving like that, okay? So like that, okay? Still, everything is the same, I mean, relatively. So we have now the integral from 0 to -1, similarly to here. We don't really care about it. Again, you can replace everything with x with the t's or dt. Again, the main point will again only be to focus on the exponential decay. So your e to the minus I omega x. That will be your main focus point, okay? So you will again replace your x with r times e to the pi I t, and you will use Euler's formula. Yes, and yes, so you will have this at the end, so you will take your minus I here and multiply it with the stuff inside Euler's formula. So I mean, at first you should get like e to the minus I omega r e pi I t, and then you get e to the minus I omega cosine pt plus I sine pt. Okay, I hope you can read it. So e to the minus omega times cosine pt plus I sine pt. Now you can take the minus I inside, and you will get what is written here. There should be an I here. I will rewrite it maybe. You will get e to the omega, I have forgotten my r, so it should be an r here, e to the omega r times times minus I cosine pt plus minus I times sinus of pt. I hope you can read it. Okay, so this is minus I squared, okay, minus I times I, so minus I squared, and so minus I squared is minus 1, so plus 1, okay, so this will give us just a 1, okay. That's why we have a positive sign here, okay. It's because we have negative I squared, so positive 1, okay, so negative 1, so positive 1, okay. And here there should be an I here, yeah, there's a negative sign, but not the I, that was missing. Now it's here. Okay, so now we remember that omega is positive, and also that sign of pt here is negative for all values because we're in the lower half plane, and that sign of pt is negative for all values of t between 0 and -1. Okay, that is very, very important. Okay, so like if you take sine of minus pi over 2. That would be like here somewhere. Okay, so if we rotate, it would be like here in the middle. Yes, so it's always negative. So that's a good sign, because I said omega is positive, but we need something negative in the exponent to get or e to the minus infinity. So the minus sign will come from the sinus, okay? But again, it's good to not have two minus signs. If omega would be negative, sign would be positive, because if both were negative, you would get a positive, and you won't get any exponential decay. So that's not what you want, okay? So omega is positive, so sign of pi t should be negative. And again, remember that the e to the minus I cosine pt is bounded, because there's an I here. So it's something of the form e to the I theta, and we know that something e to the I something is bounded. So we don't care about cosine again. And remember, our radius tends toward infinity, positive infinity again, because a radius cannot be negative. Remember that, this is a geometrical distance. A geometrical distance cannot be negative. So our radius will always tend toward positive infinity. So now we have a positive omega, a positive infinity radius, and a negative sign. So we get e to the minus infinity. That's what we wanted. Okay, so we get our exponential decay here, so e to the minus infinity, which tends towards 0. And that's what we wanted. Okay, so now we have our we have proved that our second part again vanishes if the radius if the the radius r tends toward infinity. And so we're only left with the first part, which is our original integral, okay? So we know that our original integral, so our contour integral is equal to our original integral plus 0. And now it is equal to negative 2 pi I times the sum of the residue. Again, negative, because we are in our contour integral is in a clockwise direction, okay? Before, in the first case, we are in counterclockwise direction, because we go from negative infinity to a positive infinity, then we go like that. So that's counterclockwise, so it's positive, as in here. But here we're clockwise, so it's negative. Again, this has no mathematical, no real meaning. It's just the mathematicians that agreed to do like that. Okay, so clockwise is negative, counterclockwise is positive. Okay. So it's minus 2 pi I times the sum of the residues. Again, we only have one residue inside. We have it for the pole minus 3 minus 2i, okay? Because the minus 3 plus 2i would be in the other part, so the first part, okay? So we only have minus 3 minus 2i. And so now we can, we can evaluate our residue. So we have minus 3 minus 2i as a x. So this residue here. And so we can evaluate it. We can multiply with minus 2 pi I, and we can rearrange it, and we should get pi over 2 times e to the minus 2 plus 3i times omega. And here again, I hope you can read it, we assume that omega is positive, so greater than 0. Yeah, so that's it. Again, it's an example. I hope it was clear and that you could read most of it. I should really improve my writing now. So again, the main focus on this video is to evaluate a Fourier transform using the residue theorem. So again, what you do first, let me change color maybe. What you do is you find your poles as usual, and then you calculate your residues for all different poles. Okay, so here we have 2 poles. First, of course, you notice if you have a pole of order 1, in which case you can use this formula, so h of x over g prime of x. So you simply take the derivative of the denominator. But if you have a pole of higher order than 1, you should use the general formula that we used in 1 or 2 of the videos that I did yesterday or this morning, if I remember well. So if you have something squared or to the 3rd power or whatever, here we have it easy. And generally in exam you don't have something higher than the 2nd or 3rd pole, because after that, I mean, if you have something to the 89 power, you can't do that by hand. You need a computer. I mean, it's impossible to show that in an exam. But maybe, I don't know, maybe you will see that one day. I don't know. But here it's of first order, so we can use that formula and take the derivative of the denominator. Yes, and then we need to make the case difference to evaluate it differently depending on the sign of omega. If omega is negative, we to prove that the second part later goes toward 0, so that we have an exponential decay, we should make sure that the sign of pt will be positive, okay? And so we need to evaluate it in the upper half plane, where the sign generally along the imaginary axis will be positive. If omega is positive, the sign should be negative, so that again we have a negative sign, okay? And we can remember that the radius will always tend toward positive infinity, because we cannot have a negative geometrical distance. Okay, the radius is a geometrical distance, and so it's not really possible to have a negative distance. Yeah, so that's all the deal. Depending on the sign of omega, the sinus of pt will have a different sign. Okay, we'll have the opposite sign. And then again, the rest of the proof, we don't really care about the dx, dt, or the x squared. You can write them on the paper, substituting x with re pi t and dx with pi I r e to the pi I t dt. But really, you will focus on this e to the minus I omega x, okay? This here. Yeah, so then once you have proven that your second part vanishes, so that you got your exponential decay, and remember that e to the minus cosine pt is bounded. Remember that, so we don't care about it. Because it's e to the I something, so I theta basically. Yes, and once you have done that, so you have proved that your second part vanishes, so you're only left with your first part along the real axis, which will be your original integral, and then you can use the residue theorem. So remembering that if it's 2 pi I, so positive 2 pi I, if it's counterclockwise, which is the case here for the first scenario, times the sum of the residues, so the residues that are inside your domain again. So here it's minus 3 plus 2i, and so you can find your final result. And of course, don't forget to write that this is if omega is negative in this case. So don't forget to write that this result is only valid for a given sign of omega, if it's positive or negative. And then for the second part, you do the same thing. Similarly, you again prove that the second part, so the part along the circular axis, vanishes, and so you're only left with your original integral, and then you can again use the residue theorem. This time noting that here we have a clockwise direction, so we have a negative sign here. Okay. And then you get your second result, and this time also you note that this result is also dependent on your omega. Okay, here omega is positive, and thus you get this result. Okay, if you write nothing, sometimes in exams you lose a few points. At least it was the case where I did my exam. So better to write it. And so also for the understanding, it's generally better, so you know what you're doing. Yeah. So I hope it was clear, and thanks for watching, and I hope I forgot nothing, and that I should really improve my writing. I know. I hope you could read it. But still, I'm talking most of the time, so it should you should understand what I'm saying. But still, thanks for watching.